Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Sure. I'm David Coates from Dartmouth College, and I'm happy to talk to you today. I'm really pleased that Microsoft put together this event, and it's been very interesting so far. I'm going to talk about wireless networks and measurement in particular, and this is a little bit of a mixture different from the previous talk in the sense that I have a few results, but mostly I'm focused on challenges. Obviously, we're faced with a lot of wireless devices. One of the speakers this morning mentioned this clear trend towards the users of your campus network being primarily laptop users, primarily wireless laptop users, and increasingly handhelds and other devices. In fact, at Dartmouth, where we require all students to own a computer, we passed the point a few years ago where no students are buying desktops anymore. Not a single student chose to purchase a desktop as of about 2 years ago. They all buy laptops, and we only sell wireless laptops. We've had an all-wireless, an all-campus wireless network for several years. And of course, this means that there's a lot of wireless traffic. And in order to manage and monitor that traffic, you need to be able to measure it. And I'm going to focus on the measurement issue this afternoon, excuse me. And there are many reasons why you might want to measure a network. Certainly, as a researcher, I'm very interested in learning about wireless networks, the way people use wireless networks, the way the networks behave under different kinds of workloads. But from an operational point of view, obviously you'd like to understand what's happening on your wireless network. You want to be able to notice when people are misbehaving, either maliciously or due to misconfigurations. And you'd like to be able to obviously detect certain kinds of attacks that are trying to degrade the quality of your network. You also need to use measurement for capacity planning. If you want to understand where you're having coverage problems or load balancing problems, you need to measure it in order to plan for the future. Now, of course, wireless does have characteristics that are very different than wired networks. You can't just use the same tools that you might use for wireless network, for wired network measurement. In particular, the usage patterns are very different. There's obviously a lot more mobility and different kinds of connectivity in the network structure itself. And so there are several components to this talk. The first is, and the bulk of it's about measurement. And then there's a difficulty or some challenges related to merging the traces that you collect in a large-scale measurement problem. Then you have to analyze the data in some way, and I'm only going to talk about that as it relates to the quality of the measurement. And then hopefully you want to publish the data that you've collected in some form. As a researcher, of course, I'm interested in academic publications. I'm also interested in sharing and making the data available to other researchers who are interested in data. But as someone mentioned earlier today, there's a need to publish and share data that's collected about your network with other parts of the campus or with other campuses or other enterprises that may be experiencing similar challenges. So let's look now at some of the challenges specific to wireless network measurement. We've found that it's not nearly as easy as you might think. Now what I'm talking about mostly here is packet capture, or actually frame capture, trying to capture the frames that are traversing your wireless network. When we started doing network capture at Dartmouth on our wireless network, we plugged the sniffer into the Ethernet switch, much like Mort was just describing, and captured all the frames that were flowing over the Ethernet. Now we're trying to capture the frames as they traverse the air itself using air sniffers. But hearing all of the wireless frames is actually pretty hard. You're listening to radio signals, and radio, as we all know, is very finicky with the differing ranges, reflections, multipath, loss, and so forth. It's not necessarily the case that even if you put a sniffer right next to your access point, that you'll hear everything that the access point sends or hears itself. The data flows can be fairly large, certainly nothing compared to what you might capture on a backbone link or something like that. But if you're capturing from many channels on a single, in a single area, you can get up to 54 megabits today. And with the next generation wireless networks, that's increasing. But the biggest challenges really relate to the lack of tools. There are very few tools that are portable, that apply to many different vendors of network interface cards, for example. There are very few standard formats. Of course, the PCAP format used by TCP dump and related tools is a standard, but if you're capturing at the at layer 2, all of the 802.11 headers and so forth, there's still some uncertainty about which formats are likely to win out in the long run. And then finally, the driver interfaces in many cases are not open. We've had a great deal of difficulty of getting low-level information out of many network drivers because the APIs are not available to us. Furthermore, the networks themselves are becoming more complicated. Modern access points are constantly adjusting their configuration in response to changing conditions. They're changing their channel assignments, they're changing the power levels of the access points, and that makes it harder to know where to put your sniffers and how to configure them to capture the traffic. So as I mentioned, when we did our first packet captures back in 2001, when our network, our campus-wide wireless network was brand new, we were measuring the wired side of the access points. And that enabled us to very easily sniff quite a few access points, maybe 20 or so access points with one sniffer. It was just a Linux box running TCP dump. The problem is that you only see traffic that's bridged from the access point, by the access points from the wireless side to the wired side and vice versa. Any data that goes between clients on a given access point, you won't capture. Furthermore, you won't see any management frames, control frames, errors, collisions, and things like that are happening in the air. You won't see any traffic from some neighboring wireless network that's not related to the SSID supported by these access points. And you only see 802.11. If you're interested in understanding interference due to Bluetooth or other traffic in that frequency range, you can't do it this way. So we've been focusing on building better tools for sniffing the air. And in this picture, now I just have one access point, and you notice I have 4 sniffers. One of the challenges here is that you need a lot more hardware in order to capture the same amount of traffic. And that's because, of course, your sniffer's placement is out there in the field with the clients and not in the switch room. And in fact, because the clients are spread around quite a large area sometimes, you have to have more than one sniffer per access point, especially if you want to be able to hear clients that maybe aren't in range of the access point or are having trouble, or clients that are just on the edge of the access point's range. So there are tools for wireless sniffing. Most of them to date have been focused on war driving. They're interested in collecting a set of beacons from access points so you can find out what access points, what networks are active in your area. Maybe use them like in PlaceLab, for example, for localization and things like that. We're interested in capturing all the data. A lot of the other ones that do capture packets or frames from the wireless network tend to be focused on a fairly limited range of activity. They might be trying to capture the data frames and don't pay much attention to the management and control frames. In fact, we found it to be quite difficult to modify the drivers to capture every management and control frame that came across. And finally, they don't scale. Most of them are meant for capturing frames for a minute or two at a time, or for some subset of the MAC addresses or some subset of the ports. We want to capture for hours, actually weeks and months at a time. Our longest packet captures are for 4 months, campus-wide. And most of the tools out there just simply can't handle that amount of traffic. They tend to just fall over and die. So we've been steadily improving our tools. Just as a case study, we tried to do some packet captures much like they're doing here today. The last time I was in Seattle, in fact, at MobiSys 2005, we had, I think, 4 boxes, actually custom-made Intel-based Linux boxes running TCP dump with 3 antennas each so that they could capture on 3 channels simultaneously. And we had a whole host of problems in that configuration. They were plugged into the wall for power, but otherwise had no network connectivity. They were all in promiscuous mode, capturing packets. And so we couldn't talk to them or see what they were doing throughout the day. And as a result, we would often find at the end of the day that the network managers had changed channels of one of the access points during the day. And so our sniffers were no longer sniffing anything of interest. And so you really need to make much smarter sniffers in order to do a better job. And so obviously you would like your sniffer to automatically configure itself to detect where the interesting traffic is and to focus its efforts on sniffing that traffic, to change channel when the access point changes channel, for example. We're also interested in protocols that might allow us to control a sniffer remotely, especially if there is no wired or other control connection to the sniffer. So some special broadcast protocol, for example, that could reconfigure the sniffers. And we haven't looked at it, but we really need mechanisms for positioning sniffers optimally. If you walk into a large space, a big library or something like that, you don't really know where it's best to put your sniffers. The obvious thing is to put them next to the access points, but that's only going to give you a certain picture of what's happening in the wireless traffic in that library. So you might want to think more about where the users congregate or where the network traffic might be most common. We don't have any good ways to do that today. So one of the things that we're trying to solve right now is channel sampling. We recognize that 802.11 has many channels. On 802.11b and G, there are 14 channels worldwide, 11 in the US, and over 20 channels on 802.11a. But most hardware has one radio, or maybe two radios. And it's actually quite difficult, as we've found, to build devices with more than two radios that are inexpensive and small and portable. And so clearly then you need to sniff across many different channels. And so we're trying to develop some sampling mechanisms that switch channels from time to time, pick up frames on more than one channel. Obviously, you can do that very simply by just rotating across the 11 or whatever channels one at a time. But we want to do this strategically to adapt to find the most interesting traffic and spend more of your time on those channels. And of course, that begs the question, what is interesting? Well, it depends on your application. In some cases, like our workload characterization efforts, we just want to capture as much traffic as possible. And so what we do is we count the number of frames we see as we're sniffing a channel. And next time around, the loop will spend more time on that channel, trying to capture more frames. But you could also focus on the number of clients. So you spend more time on the channels where there are more clients. With the number of access points, you spend more time on channels with a larger number of access points or SSIDs. Or actually, we have another project that's focused on intrusion detection or attack detection in wireless networks. And so you might focus your efforts on the channels where attack frames or other suspicious frames seem to be more common. And another final possibility is non-802.11. We have some sniffers that we've plugged, I forget what they're called, Y-Spy, I think. These cute little USB, they look like a memory stick, but they listen to the 802.11 or the 2.4 gigahertz spectrum and just tell you how much is happening on that spectrum. And we've been experimenting with spending more time on the channels where there's more heat, if you will.
David, have you any experience with the Cognio stuff?
No, I haven't. We haven't tried it, but we've heard about it. It sounds very interesting. It allows you to sample directly in the frequency range and get lots of different information about it. But I don't know much about it.
Right, I only wonder because they do. I mean, I don't have personal experience with it, but I have some people who looked at it, and it's quite good. The only issue is that it's fairly expensive at this point. Yeah. And so my question then becomes: is that are you at all constrained by any of those practical concerns, or you really don't care about it at this point? Like the practical concerns are like, if you had the money, would that affect your design decisions, or you're trying to build something, which is much more consumer-oriented type deal?
Right. That's a good question. Which is basically how much are we focused on the practical cost limitations? And certainly, at the moment, we haven't paid a lot of attention to that. But I'm well aware that many of the designs we have in mind are fairly expensive. They do require a lot of sniffers. If you really want to be comprehensive about capturing all the traffic, you need a lot of hardware today. I'm looking forward to solutions, maybe Cognios or something else that will allow you to capture many, many channels simultaneously with a small amount of hardware. Unfortunately, the cheap hardware, consumer-grade access points, doesn't even have the processor power, let alone the radios, for handling that. So this is just a general sense of our attempt to spend differing amounts of time on the channels that are more interesting. And it's a very simple adaptation. You count the number of frames or whatever interesting metric you're using, and you spend in the next cycle more or less time on each channel depending on the proportion of interesting traffic on that channel. And just to give you a sense of how this works out, here are This is an 802.11a experiment, so that there's a bunch of channels that we're sampling across here. This is the number of frames that we captured. We had 2 side-by-side sniffers listening to the same traffic, one of which was spending an equal amount of time on each channel, the other one which was using this adaptive proportional sampling. There were 4 access points on 4 different channels in the area. And not surprisingly, we captured more frames from those 4 channels when we did this proportional sampling. In this particular application, we were using it to detect network attacks. And so there were actually attackers attacking those 4 different channels. And again, very briefly, this is the total number of attack frames that we saw. And this is the varying cycle time. So you're cycling between these channels and coming back around again. The cycle time doesn't actually have that much of an effect on the results. But you can see on the 2 lower bars, the equal time sampling strategy, where you spend the same amount of time on each channel. And the 2 right-hand bars are when you're using this proportional sampling. We're able to capture a lot more of the attack traffic by spending the right amount of more time on the interesting channels. Yes?
How did you define an attack frame here? How did you identify an attack frame here?
In this particular case, well, we were looking at 3 different attacks, and I can't remember which attack that particular plot comes from, but for example, one of the attacks was a deauth. Well, we had deauth floods and what we call a deauth trickle attack, a much more subtle version of deauthentication attacks. And so the attack frames were those that were spoofed deauthentication frames. And I can talk to you about the details afterward. Very similar, I think, to actually what you guys have done. So one of the other challenges, of course, is that you have more than one sniffer. As I showed you earlier, there were 4 sniffers in that area. In order to do whatever analysis it is you're trying to do, you need to combine the results from many sniffers into one. And there are a couple different ways you might do that. But in general, what you would like to do is to merge the stream of frames coming from all the sniffers into one coherent, time-ordered sequence of frames. The challenge, though, of course, is that when in this case, one laptop is sending a frame to another laptop, that transmission might be heard by both sniffers, and therefore the frame is captured twice and sent. Both of those sniffers send a copy of that frame to the device that's combining the streams. And so we would like to remove that duplicate. Of course, the alternative is that only one of them hears it, in which case we don't have a duplicate. Or another possibility is that the frame actually was sent twice, received once by this sniffer and once by that sniffer. Those retransmissions happen in a wireless network, and in that case it's not a duplicate and shouldn't be removed. And so it turns out that this merging problem was more difficult than we expected for that reason, as well as synchronization. We'd like to output the frames in order. Obviously, the sniffers have their own clocks and are time-stamping the frames with their own clocks. Synchronizing those clocks or resolving the asynchrony at the time of merging turned out to be pretty tricky. There are a lot of implementation details and reasons for that. The clocks inside the sniffers are not as reliable as we would like. Also, detecting whether 2 frames are the same quickly and easily turns out to be more difficult than we would have liked as well. We were using the checksum essentially as a hash key, and that's not completely correct all the time. On the other hand, this merging does help. This is a graph similar to the previous one, the total number of, in this case, attack alerts. And we were concerned about false alarms. So sometimes any IDS is going to raise an alarm when you didn't have an attack. And our concern was that these duplicated frames might cause these intrusion detection systems to raise an alarm inappropriately. And when we were using this merging, the second and fourth bars here represent the merging cases. Merging reduced the number of attack alerts that were produced as a result of this system. Now, there are many kinds of analysis that you might want to do on your measured data, and I'm not going to talk about characterization or intrusion detection and things like that much here today. But one of the measurement-related questions is, how much data did you actually capture? How do you know whether what you measured is even close to what was actually happening in the wireless network at the time? We know that we're sampling across channels. And when you're not listening to a channel, you have no idea what you just missed when you weren't on that channel. Furthermore, the sniffers are not next to every client and might not hear everything. So we're trying to develop some tools that will help us to estimate how good our measurement capture was. And the approach we're using at the moment essentially is to recreate the 802.11 finite state machine to try to look for inconsistencies. If you see a data packet, a data frame and then an acknowledgement frame, you probably were able to get both of those. If you're missing the acknowledgement frame, well, either that meant that the acknowledgement wasn't sent because the recipient didn't hear the data frame, or you didn't hear it. You, the sniffer, didn't hear it. It's a little harder to tell what happened in that case. But if you see an acknowledgement without the data frame, you pretty much know that you missed the data frame. It was actually sent, but you, the sniffer, missed it. So we're trying to come up with a metric and a tool that can estimate the quality of our capture.
Question?
Yeah.
You talked about why you want to monitor in the air instead of on the wire. But have you thought of correlating with the wire traffic?
That's I see, sniffing both of them simultaneously.
And just for correlation purposes?
Yeah. I've thought about that. We haven't tried it yet. It's a good idea. Thanks. So, publication of the data. So briefly, since I'm almost out of time, one of the things that we're trying to do is to make our data and others' data available to the research community at large. We have a new project funded by NSF called Crawdad, which is a resource for you, for the research community, to get access to wireless data like ours. And if you visit our website and register, there are over 250 registered users today. We have 13 data sets online, several hundred gigabytes of data available, and more coming all the time. So to summarize, I see many challenges, some of which I have described already, and a few others that I haven't covered yet. In particular, how can we correlate packet traces with other data sources? We also collect syslog, SNMP, call detail records, radius records, and things like that from other services on campus, from the access points themselves. How can we correlate data from those sources with the packet traces and make better sense of the packet trace data that we have? How can we extract mobility models? In recent weeks, I've seen a huge number of people coming to Crawdad looking for data to build better mobility models. This is a very hot area, it seems. A lot of people want to use mobility models for their simulation experiments. And getting a realistic mobility model out of traces is an unsolved problem. And how to release data without exposing people's privacy is a big concern of mine as well. So I'll stop there and see if there's any more questions. Yeah?
So, it's obviously great to gather sniff every packet and do something with the gathered data. Obviously, there's a scalability problem. So have you thought about what you can do only with aggregate information, for example?
Yeah, we're starting to think about that. Our main goal so far has been focusing on basically the best possible sniffing system we could imagine. But I can certainly understand that for many applications, you don't care about seeing every frame. You really just care about certain characteristics. And so we're looking at efficient ways, first of all, to essentially compact the set of frames on the sniffers themselves and transmit only compacted features, and then ways to summarize maybe groups of frames or periods of time, and then again to merge those summaries. That turns out to be non-trivial. And I have seen the DARE paper, for example, and I know how you guys do it. Of course, yeah. Well, you have a specific application in mind, and it's got some nice techniques, and we're certainly aware of that. Yeah. Over here.
I'm just asking a question. When you talk about this, there's too much data to be collected. Are we talking processing has a problem, storage has a problem? What's the data volume we're talking about? I mean, on the wireline side, we know we do very pervasive monitoring is okay. So, I mean, other than, on the capturing side, we have some challenges on the wireless side. But then, once you capture them, what's the problem?
Well, you want, for wireless traffic, you want to do things like find the location of the user in real time and give some indication if there is a problem. At least for the kind of problems that we've been thinking about.
Real-time analysis.
Yes.
Okay.